All right. You guys are too relaxed for the day before exam. So the first question, is there an exam, right? We won't know until Wednesday afternoon. Assume, I mean, for your purposes, you should assume no outage, exam, right? If somehow that's not the case, then we'll worry about it then. But I don't want you to find an easy way out and say, oh, of course, power outage. These power outages have been really disruptive. Anyway, so today I'm going to start a subject that is not part of the exam. Perhaps that explains the low numbers I'm seeing in the seats. But it will be on the final, so you better pay attention. So this is almost like an exam review in the sense that Z transforms are like so closely related to Laplace transforms, except they are for discrete time signals. So everything is pretty much mimicking what Laplace transforms do to continuous time signals, except in the discrete time case. Okay? So pretty much everything I say today has some analog for, well, analog signals. And therefore, this is a great Laplace transform review as well. And as you know, Laplace transform is a good part of this exam, whenever it happens, hopefully soon. All right, so when we had a continuous time signal, we appealed to the Laplace transform, and we defined the Laplace transform to be the integral from minus infinity to infinity e to the negative stx of t dt, right? All right, so you may remember that early in the course we talked about response of LTI systems to signals like e to the st, right? We found that what came out was a transfer function times e to the st, right? What did we say for discrete time? Well, how did we characterize discrete time signals that were exponential? Something came in, so this was continuous time. And in discrete time, something came in, and h of z, something came out. What was that something? Z to the n. All right? So the complex exponent in the case of continuous time systems is e to the st. In the case of discrete time systems, it's z to the n, where z is some complex number, right? So with that analogy in mind, can you take a guess about how we might define the Z transform? So now we have x of n, a discrete time signal, and we will get x of z, and that, first of all, what should happen to the integral? It should become a summation. It should go from n equal to negative infinity to positive infinity, just like time going from negative infinity to infinity. And x of n should make an appearance, of course. And what would you put here? Z to the minus n. You got it. So this is the Z transform. Right? That's how we define it. Why is it called Z, not Laplace or some other French name or German name? We'll find out later. Okay, it's not that interesting, but I just want to raise your expectations a little. Okay. All right. So, and how do I recover the DTFT from this? What did you say? Yes, so basically you just take x of z, substitute z equals e to the j omega, and that definition, this will now be e to the negative j omega n, and so now you're going to have x of e to the j omega, same definition as the DTFT, right? So Z transform is more general. Again, the Z transform may converge for certain values of Z, right? When it doesn't, when Z is on the unit circle, when Z is equal to e to the j omega, right? So therefore, Just like Laplace transforms being a little more negotiable in terms of their convergence, so is the Z transform. So there's a region of convergence associated with the Z transform. So, and the DTFT exists. It converges if the region of convergence, ROC, contains the unit circle, because e to the j omega means you are on the unit circle, right? Don't forget the complex plane. So you have the real axis, imaginary axis, and then the circle, unit circle. And every point on the unit circle is a complex number that looks like e to the j omega, right? Because the magnitude of e to the j omega is 1, so it has unit distance from the origin. And the angle that it makes with the horizontal axis, the real axis, is omega. So omega basically parametrizes the points on the unit circle in the complex plane. Okay, so let's talk about some examples. As you can see, this is a fairly simple concept. And it's actually, you'll see that it's even easier to judge convergence because we have sequences, you know, the summation, a series, does it converge or not, so these are easier to judge usually. So here's an example. Let's say this is going to be super easy, but let's say we have the unit impulse. So at n equal to 0, we have 1, and otherwise we have zeros. Okay? What is x of z? Very simple, so don't overthink. No tricks. Well, I mean, z to the negative n times x of n, but x of n is non-zero only at n equal to 0. So you're multiplying 1 with z to the 0, which is 1, so you get 1. And what is the region of convergence? Everywhere. Doesn't matter what z is. ROC is the entire complex plane. Okay, so that was not challenging enough for you. In fact, none of the examples in this lecture are, but I don't think you'll complain about that. So another example. Now, this is something we studied when we were talking about DTFT. X of n is a to the n times u of n. Okay? And so we want to find out what the z transform is. So the signal doesn't start until time equal to 0. So when we look at x of z, we have to start the sum at time 0 and go to infinity. So it's a to the n times z to the negative n by definition. And this really looks like and 0 to infinity of this number a times z inverse, right, to the power n. Okay? So that really is like, 1 plus x squared, etc., where x is a z inverse, and also x is complex, not the usual real. Okay? So what do you remember about whether or not that series converges, the geometric series? If x has magnitude less than 1. If you allow x to be complex, the condition is the same. Still the magnitude, in the sense of magnitude of complex numbers, has to be less than 1. So it is equal to 1 by 1 minus x if x has magnitude less than 1. Therefore, since our x is equal to a times z inverse, we're going to get 1 minus 1 minus a z inverse. 1 by 1 minus a z inverse. All right? So there you go. That's your z transform. We usually leave the z transform in terms of the negative powers of z. You can, of course, write this as z over z minus a. Maybe it's more pleasant to look at. But we're going to leave things in terms of z inverse when we can. And you'll see why when we start doing the inverse z transforms. Okay, so when does this converge? Well, I already told you. We defined x to be AZ inverse, and we said that the magnitude of x should be less than 1. Therefore, we want AZ inverse to be less than 1. And of course, AZ inverse means the magnitude of A by Z, which is the same as the magnitude of A by the magnitude of Z, and that's less than 1. So that means our region of convergence is Z magnitude bigger than the magnitude of A. All right? So whatever A is, let's say A is real, okay, and a positive real number, let's say, okay? So this is real, this is imaginary, and let's say this is A. So what does the region of convergence look like in the complex plane? So a circle with radius A, correct? Anything outside of that. All right, so the circle, okay, came close, but not quite. By coarsening your lines, you can always fix plots. So, okay, and then the region of convergence is anything outside of that. So it's here. Okay, and again, this is supposed to be outside. What about the circle itself? So remember, this has to be strictly bigger. Okay? So therefore, we can't include the circle, so we have to exclude it. So I'm going to put dashed lines here. So that means it is not part of it. Okay? Now, if I ask you, what are the poles and zeros of this transfer function, then you would not be quite satisfied with this form, because it's hard to look at this and say, oh, here's the pole, here's the zero. It's probably better to put it in terms of a function of z, not z inverse. How do I do that? Easy, multiply both numerator and denominator by z, and you get z over z minus a. And now it's clear what the poles and zeros are. So at a you have a pole, and at 0 you have a 0. Okay? So as you can see, the ROC does not include the pole, which it shouldn't, because, you know, pole by definition is a singularity, so it shouldn't converge at that point. All right, any questions, comments? All right, I have a question. So does the DTFT exist? How do you judge that? Yeah, DTFT exists if unit circle is in ROC. And so you have, there are two possibilities. The unit circle might be inside, outside, like this, or inside like this. How do I know? Well, it depends on what A is relative to 1, right? So if A is bigger than 1, then the answer is no, because then you have this situation. If A is smaller than 1, then the ROC does include the unit circle, so then the answer is yes. Right? So that's an answer that we already knew. When we talked about DTFT, that was we did talk about the DTFT of A to the n u of n, and our condition for convergence was that A be less than 1. Okay? So if A is less than 1, the answer is yes. And if I want to know the DTFT, I don't need to compute it from scratch. I can just look at my x of z, substitute z equals e to the j omega, and I'm going to get that. Right? So 1 over 1 minus a z inverse, which is, of course, e to the negative j omega. Okay? So all set. Z transform is more general. All right, any questions? No, okay. Then let's bring in more examples. So In Laplace transforms, remember, you had a right-sided signal like e to the at, right? And the left-sided version of this multiplied by u of negative t, and they gave you the same Laplace transform. Does something like that happen in Z transforms? The answer is yes, and this example shows you why. So in this example, x of n, instead of a to the n times u of n, we're going to put a negative sign. That also was the case in Laplace transforms. A to the n, and u of not just negative n, but negative n minus 1, which indicates that the signal has nothing when n equal to 0. Okay, so it's it goes from n equal to negative 1 to negative infinity. Okay, 0 and positive n, the signal is 0, right? So the way to find the Z transform is simply to apply the definition. So you do the sum this time from negative infinity to negative 1, because the signal ends there, and I have a negative sign because there's a negative sign here. A to the n, Z to the negative n, right? If I replace negative n with n, then I can change the order of change the sign of the limits, right? So I'm going to then have from 1 to infinity, let's call it m is negative n, okay? A to negative m, Z to m, all right? And that looks like A inverse Z to power n. Okay, and there's a negative sign. Let's be careful about that, right? So this looks like the geometric series we have, right? It's going for starting at m equal to 1, not 0. The geometric series we were looking at was 1 plus x squared, etc. This doesn't have the 1. So let's give it that 1 it's missing, okay, and take it back. So basically do this. 1, add a 1, and subtract a 1. So you've changed nothing. But when you're subtracting 1, you're really extending the limit of the sum to m equal to 0, because what's in the summation is 1 at m equal to 0. Does that make sense? Do you agree with what I just did, or did it go too fast? Okay. So I put a 1 because when I include m equal to 0 in the summation, m equal to 0 gives me 1, so those 1s cancel. Okay. I want it this way because this is a series that I recognize. It is a series that will converge to 1 over 1 minus A inverse Z when A inverse Z is less than 1. Okay? So, but then I have 1 minus, oh wait, what did I do? Yeah, that's true. Okay. Oh. Okay. Yeah. Okay. All right, so then I have this. 1 minus A inverse Z. So let's simplify or match the denominators. A inverse Z minus 1 by 1 minus A inverse Z. 1's cancel conveniently. And I'm left with negative A inverse Z 1 by A inverse Z. I would like to put this in a form where Z inverse appears instead of Z. So to do that, I'm going to multiply everything with A, let's see, what am I multiplying with? Negative A Z inverse, and that will make the numerator equal to 1. Do you agree? So if I divide and multiply by negative A Z inverse, you probably won't complain. And then by doing this multiplication, I'm basically making the numerator be 1. Do you agree? Yes, give some reaction, please. Yes, okay, cool. 1 by, this also becomes 1, this times this, right? So 1 minus A Z inverse. Okay, that's our x of z. But wait, what's going on here? That's the same x of z we had here. Remember this guy? 1 over 1 minus A Z inverse. We got the same thing.
What is different? The region of convergence. The region of convergence is here. It says that A inverse Z, which is Z by A, needs to be smaller than 1. Therefore, Z is smaller than A. All right? So the difference now is the ROC. So we have the same picture, same real axis, same imaginary axis, same circle with radius A. So the radius is still A. All right? But then the ROC is really what's inside. Okay? And once again, the circle itself with radius A is excluded. All right? And again, there's a pole at A if A is a real positive number. Okay? So there's a drastic difference. I mean, the Z transforms look the same, but the ROCs are complementary. They don't even intersect because they would have intersected at the circle, but the circle is not part of either ROC. All right, so a couple more examples. So let's say, now this is just an application of examples 1 and 2, or 2 and 3. 1 was just a delta. Let's say I have this 1 over 2 to the n, u of minus n minus 1, plus negative 1 over 3 to the n times u of n. This is a two-sided signal, right? On the left side, there's an exponent of 1 over 2. On the right side, there's an exponent of negative 1 over 3. So, but from example, just the previous example, this plays the role of my A, right? And I know that the Z transform of this part is 1 over 1 minus A Z inverse. A being 1/2, I put that there. So that is the Z transform of the first piece, right? And the ROC for that part is Z smaller than what? A, which is 1/2, right? Okay. What about this? This is the earlier example, the right-sided example. This again is our A. So it's going to again look like 1 over 1 minus A Z inverse, but A is negative 1 over 3, so this will make it a positive Z inverse. And now Z must be bigger than 1 over 3, right? Because for right-sided, the ROC says the magnitude of Z is bigger than the magnitude of A, which in this case is 1 over 3. Okay, so the rest is easy. You can just simplify that. So basically you have the sum of those two, and that's equal to, if you do the simplifications, and if you multiply both the numerator and denominator by Z square, you're going to get 2Z. I mean, you do that to avoid Z inverse. And we want to avoid Z inverse when we're looking at the poles and zeros of the Z transform. So it's going to look like Z minus 1/2, Z plus 1 over 3. All right? So let's make a sketch of the region of convergence again. So we have the real, imaginary, as usual. And where are the poles? We have a pole at negative 1 over 3. We have another pole at 1 over 2. That's a positive one and bigger in magnitude, right? Is 0 at 0, and is 0 at 1 over 12, which is a pretty small number. Zeros are not a big deal when ROCs are concerned. So we're going to get a circle here. Let's make a circle. So the ROC is what? So it has to be the intersection of this and this, right? And what is that intersection? It's a sort of ring. Yeah, there's a fancy term for it. But so it is the exterior of this circle. That wasn't supposed to be done. Okay, you can endlessly obsess with these things. Anyway, So, yeah, so the inner circle has radius 1 over 3. Right? Okay. 1 over 3. Okay. And the outer circle has radius 1 over 2. And you have to be less inside the outer circle, but outside the inner circle. So that gives you this region as the ROC. And as you can see, the poles are again on the boundary. The ROC just can't include the poles. It just goes against the definition of poles. All right, so that's the picture. If I ask you whether or not this function has, this sequence has a Fourier transform, your answer would be? The question is the same as asking, is the unit circle, radius 1, inside or outside this ring? It's outside, so DTFT does not exist. Or the DTFT integral does not converge. All right? All right, so, okay, what if I change the problem a little bit, and I'm not going to work this out in detail, but what if I change the problem to the following? 1 over 2 to the power n, u of n. So what if, and minus negative 1 over 3 to the n times u of minus n minus 1. Okay, what would be the answer then? I mean, what would the Z transform look like? It will look exactly the same, right? Just by those two examples we discussed, they give you the same Z transform. The question is, what is the ROC of that? The ROCs in this example would turn inside out. So you would want Z to be bigger, not smaller than 1 over 2. And you would also want it to be smaller, not bigger than 1 over 3. And the intersection of those two is nil. There is no such intersection. You can't be smaller than 1/3 and bigger than 1 over 2 at the same time. So the ROC in this example is the empty set. All right? So there is no Z that pleases this summation in the definition of the Z transform. Similarly, I can take, this is the latest example and last one pretty much. Similarly, I could take a two-sided signal that's simply a to the n. A to the n, and to make it interesting, let's say is not 0, right? Otherwise, it's all 0. So you could say, well, I can split it into two pieces where I know the Z transform of each piece. You can say first the right-sided version, and then a to the n u of minus n minus 1. That way, you have a to the n times u of n plus u of negative n negative 1. That is the whole, that is all ones, right? So the signal can certainly be split in this form. And each has a transform like 1 over 1 minus a Z inverse. But then for this, the ROC would have to be bigger than a, right? Whereas for that, you would have to be smaller than a. Again, their intersection is just empty. So ROC is empty. Is that still the symbol for empty set? It was when I was going to elementary school. Okay. I haven't seen it much since. I see it now and then, but not often. Okay. So we made some observations about the region of convergence. There are a bunch of, if you look at that book by Oppenheim and Wilsky, section 10.2, they go through resilient properties of the region of convergence. If I went through those, you would be going to sleep pretty soon. So what is important is to make a few observations from the examples. So the first observation, look at this, that, and that, right? So the ROC, you have a question or? Yeah, this one?
This one? What did you say? Oh, this one. I think you got, I neither followed the answer nor the question, but I think you're happy. Okay. All right. So some observations about the ROC. It's either a ring, like in this example, or it's the interior of a circle, as in this example, or it's the exterior of a circle. Okay. So basically, all these three examples covered all possibilities. It does not contain any poles. Clearly, it didn't in these examples. If the signal is right-sided, and that will be most of the types of signals that will be interested in this course, then it's the exterior. Now compare this to the Laplace transform. Remember, this is also a review class. So in the Laplace transform, the ROC was to the right or left of a vertical line, right? So it's similar. So when you go from Laplace to Z transforms, vertical lines turn into circles, basically, right? So in the Laplace transforms, a right-sided signal would have an ROC that was to the right of the rightmost pole. And now, in this case, for a right-sided signal, the ROC is outside of the ball, the circle that crosses the biggest pole, all right? So just some observations. I don't think they are that consequential, but it's good to know, at least in the examples, what they are. All right, so that's the Z transform. We can also do inverse Z transforms the way we did it. Again, in this course, just like I said for Laplace transforms, there are ways to leverage complex analysis to give fancy formulas for inverse transforms. You basically do some line integrals, whatnot. Same thing goes for Z transforms. But we are avoiding those because, for the most part, we are interested in rational Laplace and Z transforms. That means it's a polynomial by polynomial. For that case, there is a simple method, which is the partial fraction expansion, and that's the focus in this class, not the more complicated inverse formulas. So inverse Z transform by partial fraction expansion. So let's start with an example, and we'll end with an example. There's nothing more than examples here. So let's say we are given a Z transform that looks like this. It's already factorized for you to make it simpler. 1 over 4 Z inverse, 1 minus 1/2 Z inverse. Okay, so I'm going to do a partial fraction expansion like this. A1 by 1 over 1 minus 1 over 4 Z inverse plus A2 times 1 minus 1/2 Z inverse. Okay, why do I do it in this way and not the way I did for Laplace transforms? It looked kind of prettier, right? We had this numerator in S, denominator in S, and I broke it into terms like A over S minus 1, A over S minus 2, or whatever, things like that, right? Why am I leaving it in terms of Z inverse now? Well, the whole purpose here is to be able to look at these terms and say, oh, of course, that comes from 1 over 4 to the n u of n, right? And for a of n u to the n, this is our example, we know that the Z transform has this form here, right? So we kind of try to make the terms in our partial fraction expansion look like this. If I went with the Z expansion, then I would have to turn them into pieces that look like Z over Z minus A, right? That's not very natural, so that's why we keep things in terms of Z inverse terms. So Z inverse becomes our variable in a sense. Okay? So let's see what this gives us. So the other question is, of course, how do I get A1, A2? One way to do so is to match the numerator and denominator to
the corresponding terms. You can always do that, matching coefficients of numerators, etc. But there's actually a simpler way, and look at what I'm going to do. If I multiply x of z with one of the terms in the denominator, let's say this one, x of z times, actually let me put it on the other side, 1 minus 1 over 4 z inverse times x of z, right? What is that equal to? Do you agree?
Because you canceled one of the terms in the denominator.
Now that that term is canceled, I can substitute here z equals 1 over 4. That is, put z equals 1 over 4 here. All right? So, and what is that? Can someone tell me? One minus 2, so you get negative 1, right? Okay? So why did I do this? Which of these two terms does that give me? A1 or A2, and why?
If you look at the expansion, right? Multiplying this expansion with 1 minus 1 over 4 z inverse will give you A1 plus 1 minus 1 over 4 z inverse times the other term. But when I substitute z equals 1 over 4, that other term disappears. Does that make sense? With this one? No, but because there's a cancellation, there's also 0 in the denominator, so they cancel out.
All right, so if you do the same multiplication here in the partial fraction expansion, right? So this times 1 minus 1 over 4 z inverse is A1 plus 1 minus 1 over 4 z inverse times A2 over blah, 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 right? So when I put z equals 1 over 4, this becomes 0, so that term is killed, and what remains is A1. So that's a quick and dirty trick to find A1. So you can just write this, and you found A1.
The left-hand side has 0 by 0, but that's when you cancel those, you know they were the same terms. Cancel first and substitute z equals 1 over 4. Well, look at the expansion, right? So this expansion, this whole expression is meaningful when z is not 1 over 4 anyway, right? So I'm just showing you a small trick to get A1. If it pleases you more, go ahead and match coefficients. That's not going to fail you. Okay? I'm just cutting corners because I don't need so much time. Okay, how would I find A2? In the same fashion, I would now multiply by 1 over 1 minus 1 over 2 z inverse x of z, because if I do that, A2 would come out, this would cancel, and this, to get rid of this term, I would substitute z equals 1 over 2, right? 1 over 2, and the result is 1 over 4 z inverse when z equals 1 over 2. So I think this is 1 over 1 half, right? So that's 2. Okay? And that's consistent with my notes. So that means x of n can be one of many different combinations. So we found A1 to be negative 1. I'll have to copy this here. So x of z was negative 1 over 1 minus 1 over 4 z inverse plus 2 1 minus 1 half z inverse. Okay, so one possibility when you go back would be to say, well, this comes from 1 over 4 to the n u of n. Oh, negative sign too, because there's a negative sign here, plus 2 times 1 over 2 to the n u of n, and that's x of n. All right? So that's one option. That option is consistent with what? ROC.
So that will be the answer if I told you the ROC is, where are the poles? Where are the poles? 1 over 4, 1 over 2. So if the ROC is outside of the biggest pole, which is 1 over 2, right? If I told you this is the ROC, where 1 over 2 is the outer limit, outer radius. What am I doing? 1 over 2, okay. Then this is the answer, right? Can you give me one more answer? Maybe a left-sided answer now? One over 4 n u of negative n minus 1, right? And then negative 2, 1 over 2 n u of minus n minus 1. So in this case, the ROC is drastically different. It is inside of what? What's the radius of the circle? You have to be smaller than both, right? 1 over 4 and 1 over 2. So you'll have to go with the smallest of the two. So it's 1 over 4. So it's this circle here. It's inside of that circle, right? Okay. Another option would be to be inside 1 over 2, radius 1 over 2, but outside 1 over 4. Inside 1 over 2 means this term here is going to give us the left-sided version, which is this. And the right-sided version would be coming from the other part. So that is going to be negative 1 over 4 to the n u of n. So now we want to be outside of 1 over 4, but inside of 1 over 2. So it's now a ring. Okay, not the perfect ring, but close. How is it now? Okay, so then this would be our region of convergence for this answer. So the inner radius would be 1/4. The outer radius would be 1 over 2. Okay? There is a third answer. So this is 1, this is 2, this is... No, there's a fourth answer, which doesn't make sense. What is it? It's the other combination, right? 2 times 1 over 2 to the n u of n, and 1 over 4 to the n u of minus n minus 1. Now you would ask that the ROC be inside of 1 over 4, outside of 1 over 2. There is no intersection of those two regions. Okay, so for that reason, I'm not even writing that as an option. Okay. So this expansion works in situations where the numerator has degree smaller than the denominator, because then if you look at this and think of z inverse as your variable, so if I'm able to expand like this, some a or something minus z inverse, right? If I put those things together in the numerator, the highest term would be z inverse, right? But in the denominator, I'll get z to the negative 2, right? So if you have distinct poles, that is, the denominator can be factored into these first-order terms where the coefficients a are different from each other. And if the numerator degree in z inverse is smaller than the denominator degree, you can always do this expansion. Okay? So to generalize, x of z, if x of z is given like this, b0 plus b1 z inverse. Note again, unlike the Laplace transforms where we wrote things in terms of powers of s, we are now writing things in terms of the negative powers of z because we found that convenient for the inverse transforms. Okay? So m is the highest negative order you get. And then n, let's say, is the highest negative order you get here. Okay? If m is smaller than n and poles are distinct, so there are no repeated poles. Poles are, of course, the roots of the denominator. So let's say the poles are d1 to dn. There will be n roots, and let's say they are distinct from each other. Then I can say, I can always write this as a1 over 1 minus d1 times z inverse. Do you agree that this term itself has a pole at d1? If z becomes d1, then the denominator is 0, right? And then you go all the way to an by 1 minus dn z to the negative n. All right? So that works when you have distinct poles and m, the highest power here, is smaller than n. If not, you may have to do some pre-processing to make it look that way. So let's say, let's look at that case, and I'm not going to go to the case where m is bigger than n, but I do want to tell you what happens if m is equal to n, okay? Is that a good compromise? And m bigger than n is in the note, so you can look at that. It's very simple anyway. But so let's say m is equal to n. So this no longer would work. Why? Because if I try to write this, try to write this expansion in the form at the top, right? The highest order in the numerator that's possible is n minus 1, right? Because, for example, a1 will be multiplied by that and this, and there are n minus 1 such terms, right? So the highest power that this product can generate is e to the n minus 1. And you're adding a bunch of polynomials that have order highest power n minus 1, so that means m equals n is not possible. You can't generate this with an expansion like this. But you can generate it in this form. You can say this is equal to some constant plus a1 over 1 minus d1 z inverse to an over 1 minus dn z to the negative n. Does that make sense now? Because now when I try to write, collapse it into the form at the top, b0 will be multiplied with, oh, what am I talking about? Z inverse. b0 will be multiplied with a product of n such terms which can have power z to the negative n. So the numerator can now match the denominator. Make sense? Yes? All right, so then what can I, if I tell you that that this z transform came from a right-sided signal, what would be your answer for x of n? The right-sided answer, which is our default. So you will have b0. What does that give me? First example was delta of n, unit impulse, that has z transform 1, right? So I can just say the signal is b0 times delta of n, right? And then a1 times d1 to the n, u of n. And the last term would be an times dn to the n, u of n. Agree? Yes? Okay. Now, I'm not going to write anything, but I'll just ask you. So, if m, well, okay, I'll write something. If m is n plus 1, how would you go about expanding this? That b0 will no longer save you because you actually want a higher order in the numerator than the denominator. So let's keep b0 there and the other terms. But what should be added to make it possible to get a power like z to the n plus 1 in the denominator, or z to the negative n plus 1? b1 z inverse, because everything is written in terms of z inverse, right? Yes? Okay. And then, if I then ask you what x of n is, that would create, this term here would create what? Ah, that's a good question, right? Okay, let me write that here again. Suppose I tell you a separate question which is related that answers the previous question too. If I tell you x of z is 2 times z inverse, what is x of n? Think about the definition. X of z is the sum of x of n, z to the negative n. So it really looks like, you know, x of negative 1, z plus x of 0 plus x of 1, z inverse, x of 2, z to the negative 2. So it really has the form of a convolution if you like. So just looking at this expansion of x of z, of course it goes both ways. When would it really give you 2 times z to the negative 1? Answers? Yeah, or look at these terms. This should be 2, correct? This should be 0. This should be 0, and this should be 0, right? So 2 times a delta at 1 will give me 2 times the inverse. Okay? If I have, say, 1 at n equal to 2, you'll get z to the negative 2. Just like a single impulse at n equal to 0 gave us 1, right? Anyway, so going back, now you can tell me that B1z inverse was simply B1 times delta centered at 1. That is this, right? You agree? Yes? Okay. There's an example in the notes, but we need not go through that. Let's take a break. Let's take a, huh? What did you say? Yeah, everything else is 0, of course. You talking to each other, or are you asking me? All right. All right, take a break. Actually, I need to change the battery. So anyway, I asked him about the history a little bit. So he wrote a very long email. He said that, yes, he was one of those who introduced it. He said he works with Regazzini. He was his advisor. Actually, he said he published it with Regazzini, and then he had a few remarks about Regazzini, which I censored. No, it was him who did it. It's not unusual with professors and advisees. And then the answer to the question of does that have to do with Zadeh? The answer is no, unfortunately. That's a letdown. So that's not a very juicy story. He said they called it Z because in complex analysis literature, Z was the standard letter for a complex number. Okay, too bad. So no sensational story there, and no names attached to it. So we'll just have to live with Z. At least it's the last letter in the alphabet, so that makes it somewhat interesting. All right, but it's kind of cool, right? So, I mean, it's not that old. I mean, it's old, of course, 80 years since the 50. No, I can't do math anymore. 70 years almost since that time, 60, 70 years. But in the grand scheme of things, it's not centuries. It's relatively recent. Okay, so when we were talking about the partial fraction expansion, we made the assumption that we don't have repeated poles, right? So how do we deal with that? So do you remember what saved the day in Laplace transforms? Like if we had 1 over s plus 1, we could say, yeah, that comes from e to the negative t u of t, right? But what if we had s plus 1 squared? What property? This is now exam review. Okay, what property came in handy? Not common. Huh? Wait, what? Oh, convolution in a sense, yeah, because you can convolve e to the negative t with itself, but that doesn't really save the day because that's also a complex operation, right? I mean, how do you do the convolution unless you really want to? But you remember the derivatives of the Laplace transforms were related to multiplying the time signal by t, right? So the property was, you should know this better than I do at this point, but negative t times x of t, I think, gave us d by ds x of s, correct? Okay. So turns out there's a similar property for z transforms, and that will be useful if we have repeated poles. So if I have something like 1 over 1 minus a z inverse squared, how do I deal with that? So we're going to get the answer for that now. And that property is called the differentiation in differentiation property. We're differentiating the z domain, of course. So if we have x of n, a sequence giving us x of z, then n times x of n, which is analogous to t times x of t, is going to give us z times dx of z dz. It's slightly different, of course. You know, we didn't have that s times dx ds, so it's different because that comes from the summation. Oh, there's a negative sign as well. So let's see where this comes from. That's the property we want. The proof is simple. So x of z, by definition, is the sum x of n, z to the negative n, and negative infinity to infinity. Okay? So if I take the derivative, then dx dz is, what happens? Z to the negative n gives me a derivative of what? Yeah, negative n, z to the negative n minus 1, right? So that means I can factor out negative z inverse out of this sum, because the sum runs over n. Things that don't depend on n can be factored out. And what remains inside is the sum from negative infinity to infinity of n times x of n times z to the negative n. This is the term that I'm after, because that is the z transform of n times x to the n, right? Including the negative sign. That's this term, right? And that's related to dx dz with this. The only term we're missing is this. So if I multiply both sides with z, I get z by dx dz equals, that z cancels, so I get negative n x of n z to the negative n. The right-hand side is the z transform of negative n times x of n. And the left-hand side tells us that that's equal to z dx dz. So this is proven, right? So how can we make use of this? Well, if I look at things I know, like a to the n times u of n gives me the z transform 1 over 1 minus a z inverse, right? So then negative n times a to the n u of n will give me the z times, let's not forget that z, d by dz of that. And what is this? Is anybody alert and awake enough to do this? I'm not, so that's why I'm asking you. Huh? Don't be shy. It's okay to. I can't even start thinking about it. So, chain rule, right? We can do chain rule. Let's first take the derivative with respect to z inverse. What would that be? Negative a by 1 minus a z inverse square, right? I think I already made a sign mistake. Negative a would come from this, but then because of negative 1 power becoming negative 2, this will come. And then d by dz of z inverse, right, by chain rule. Is that chain rule? It is, right? Chain rule, okay. And then there's z. Okay, and that is what? Is that it? And you're telling me I made no mistakes? Somehow I'm suspicious of this. Oh, yes. Okay, so that z will cancel with the second term, the second power of this. Okay? So you get negative a from this and this by z, 1 minus a z inverse squared. Okay? So to clean it up, you can put in the numerator negative a z inverse and 1 minus a z inverse squared. Now there was a negative sign here, so let me make that positive and this positive. So we found that n times a to the n u of n will give us this z transform. Okay? So that is a useful term. And if you are patient, you could do second derivatives and whatnot. I'm not going to do that. But let's say you have a pole of multiplicity 2. So instead of, 1, so you have an x of z that looks like, 1 minus dk. The kth pole is somehow repeated, okay? And then other poles and other stuff, right? So when you're expanding this, it is not going to be enough to say ak over 1 minus dk z inverse, because you actually have a second term. It also will not be enough to square this, because you need more expressiveness in your expansion. So you need another term, dk z inverse, that includes the square. But remember, when we are doing the expansion, we want to do the expansion in a way that each term is a pleasant one that we can immediately recognize as the z transform of something simple, right? So this fits the bill, because that comes from dk to the n u of n, right, times the coefficient ak. But for this to look like something we know, we would have to include also something like this in the denominator, right? So that means we will have to include let's call this ak1, because that came with power 1, and ak2 times dk z inverse. Okay, so we look for an expansion like this. Why? Because this term is easy to recognize, right? It comes from n times dk to the n times u of n. So this is ak1, ak2, dk to the, oh, I forgot the n times dk to the n, u of n, right? So that's how we should go about the partial fraction expansion if we have repeated terms. All right, do I dare do this? I will. Okay, so an example of doing this. So we are given x of z. It is equal to negative 1/2 plus z inverse. 1 minus 1/2 z inverse square. Okay, so let me give you a second to think about it. So how would you split this into two? So according to what we have here, it would be a11 times something plus a12 times something. All right? Why don't you take a few minutes, do this, while I get some water and come back, okay? So two tasks. First, fill in these, what should these two terms be? Second task, simplify and match coefficients. And I want an answer when I come back. I want my a11 and a12 as well as what these terms are, okay? All right. Okay, so can you tell me what the first term is? 1 over, well, first, what are the terms that I should fill in with, right? And this one should be, and what do you put here? Just positive 1/2, right? Yes? Okay. So did you do your homework? Did you find A11, A12? Which one? A11 is? Are you sure? And A12? One half, okay. That's consistent with what I have, okay. And A12 is 3 over 2. No negative sign, right? Okay. So if X is a right-sided signal, then the answer is X of n negative 1/2 1/2 to the power n plus 3 over 2 n times 1 over 2 to the n, all of them multiplied with unit step, meaning that nothing starts before time equal to 0. Okay, there you go. You've done. You're done. You found it. You're all good. Okay. So what else do I want to tell you? Oh, lots of other things. Okay, so let's now look at the notes. There's a table in the notes that, not these notes, that shows you the usual suspects in terms of Z transforms. Okay? A list of things we should sort of know about. I mean, the few at the top we should know. The others we should be ready to look up if we are solving the homework or something. So delta is 1. We know that already. If the delta occurs at time equal to m, then you get z to the negative m. Unit step is simply the case where a is equal to 1. So it gives us 1 over 1 minus e inverse. A to the n we did, either right-sided or left-sided. Now we just did n times a to the n. And there's also a left-sided version of that, which I'm not going to go into, but it's listed there. What else? Oh, cosine and sine, they can be derived from basically a to the n u of n, because a is now a complex number. So in our derivation, there was no restriction on a. It could be real or complex. So if it is complex, then we can use that to recover cosine and sine using the usual expansion of cosine, right, and sine. Okay, so that's how those other expressions are derived. So I'm not going to make a big deal of that, but it's good to have a table that summarizes them. All right. And then Z transform has a bunch of similarities that look like the properties to the Laplace transform. It has properties that are similar to those of the Laplace transform. Linearity is the usual thing. I'm not going to talk about it, but let me ask you a question. So if I tell you that x of n gives me a Laplace transform, or not Laplace, Z transform of x of z, okay, then if I delay this signal or shift it by, let's say, n naught in integer, what happens to this? Any volunteers? So what's the Z transform of this shifted signal? So that's the time shift property that I'm asking you about. Well, you can work that out. So you're doing a summation, right? By the definition of Z transform. You're summing from negative infinity to infinity x of n minus n0 times z to the negative n, right? Now the question is, can I somehow make this look like the Z transform of x of n without that shift by some manipulation, so I get an expression that depends on x of z? What did you say? Oh, define n minus n0 as a dummy. That's a great idea. So let's call this I don't know, m. Okay? So that means when we see an n in this expression, we're going to replace it with m plus n0. Okay? So that means the sum now goes from, as n is going from negative infinity to positive infinity, m is also going from negative infinity to positive infinity, so that doesn't change. It's only shifted, but shifting infinity doesn't change anything. And then we have x of m, z to the negative n, that is m plus n0, right? So if the first term here is z to the negative m, the second is z to the negative n0, right? Z to the negative m is good because it makes it look like the z transform. The other term, this one I can just factor it out. So you get z to the negative n0 times summation over m, x of m, z to the negative m. Okay? And that is the same expression as x of z. So we found the answer. The answer is basically, I'm going to squeeze this here. This will be z to the negative n0 times x of z. All right? So that means if you already know the z transform of a signal, shifting it will simply multiply that z transform with z to the negative n0, where n0 is the amount you shifted to the right by. Okay? All right, so that means, in particular, that if I'm thinking about delaying the signal by 1, that will give me z inverse x of z. If I delay it by 2, I'm going to get z to the negative 2 times x of z. So when we see in our z transforms an expression like z inverse, a multiplier like z inverse, that simply means a delay. Okay? And later on, we will see some block diagrams of these signal or some LTI systems where to signify a delay, we'll just put in a z inverse. So that will be our code word for delay. Okay? Because z transforms give us z inverse for delay. All right, so, and you may want to also compare this to similar properties of the DTFT. So do you remember what we had for DTFT? If x of n gave us x of e to the j omega, what would we have for the delayed one? Wait. E to the negative j omega n 0, right? And not, right? Each delay meant multiply by e to the negative j omega, right? X of e to the j omega. That kind of makes sense because that really is like z inverse, right? Because z is e to the j omega. When you want to get the DTFT from the z transform, you substitute z equals e to the j omega, unit circle. So it's consistent with that property. Okay, so that's a useful property. Here's an example, again, a partial fraction expansion type of example that tells us why it's useful. So, in our expansions, we talked about distinct poles, but we didn't talk about the case where you may have a z inverse in the denominator. Okay? So obviously, the first term here is not something I can write as 1 minus a z inverse, right? So we have to somehow deal with that separately, right? So how do we deal with this? Well, I can just say this is the same as z times 1 over 1 minus 1 half z inverse. And then I can say, well, I recognize this. This came from 1 half to the n u of n, right? If it's right-sided. And then if the z transform is that multiplied by z, what is the actual signal that does that? Multiplication with z means shifting to the left. Now it's an advance. Z inverse was delay. z moves to the left, it advances the signal. So n becomes n plus 1, right? So it will become 1 over 2 n plus 1 u of n plus 1. That's it. You're done. So that gives us an extra degree of freedom in doing partial fraction expansions. All right. So one more property, useful again. Scaling in the z-domain property. So let's say, again, you have x of n, it gives you x of z. And then let's say I take any number, could be real, complex, any number, and multiply, let's call that number z naught, okay? Multiply x with the nth power of that. Okay, what is the z transform of this? Well, if I try to compute the z transform, I'm going to get x of n, which looks like this now. I mean, x of n modified, scaled x of n, times z to the negative n, right? And that is the same as x of n times z by z naught power negative n. Do you agree with this? All right? So this does look like x of z, except that instead of z, I should substitute z by z0. Right? So therefore, the answer here is x of z by z0. Of course, this scaling also scales all the poles and zeros of x of z. Therefore, it also scales the region of convergence. If z equal to 1, the unit circle was in the region of convergence. Now z0, radius of magnitude of z0 is now in the unit. So it has to be scaled appropriately. All right, so this also has analogs in DTFT. If I take for z0 a point on the complex plane, e to the j omega naught, right? Then I'm talking about e to the j omega naught n times x of n. And that means we have x of z by z0, and z0 is e to the j omega 0, right? Okay, so that becomes interesting, not in this form, but when we look at the DTFT where z is equal to e to the j omega itself. What can you say then? X of what? E to the j omega minus omega naught. This is the modulation property, right? We saw this in continuous time, in discrete time. So if you multiply a signal with a carrier sinusoidal, right, its spectrum gets shifted by the frequency of that carrier signal. So in this case, the carrier signal will be e to the j omega 0 n. It's a sinusoidal thing. So it shifts the spectrum by omega naught. So that follows as a special case of this property. The familiar DTFT property is a special case of the scaling property of the Z transform. All right, so time reversal. That's kind of interesting also. Time reversal property. So if I give you x of negative n, I'll ask you, what is the Z transform of this? Knowing that x of n gives us x of z. Again, I mean, if you're asked a question like this, you should always think about the definition. So this is what you're trying to compute, right? And so to make it look like x of z, you would have to introduce a dummy. The dummy in this case would be m equals negative n. So then the sum will go for over m, x of m, z to the positive m, or z inverse to power negative n, right? Okay? So if that was z, if this term was z, then that would be identically the z transform of x. But that is now suggesting that we should take x of z for the original signal, replace z with z inverse. Right? So therefore the answer is x of z inverse. That, of course, will change the region of convergence significantly. It will turn inside out because z is being replaced by 1 over z. And essentially, this is what we saw when we were looking at the left-sided version of the exponential signal, right? So, in fact, we can recover this. Do I dare do this? Yes, I can. So, when we were talking about negative, or let's start with this. Let's start with a to the n un, right? I know that gives me 1 over 1 minus a z inverse, right? If I apply this property, then n is becoming negative n, and this is becoming u of negative n, right? So this then becomes z inverse will be replaced by z, right? 1 minus a z, or you can say gosh, how do I do this? I want to make it look like 1 minus something z inverse. Okay, let's go step by step. Multiply everything by z inverse. Or negative z inverse. So you get a minus z inverse, right? And then divide both sides by a, z inverse, 1 minus a z inverse, okay? So it's looking familiar. The only reason it looks different is that we were looking earlier at a to the n u of negative n minus 1. So there are two differences. This is not a to the negative n. So a should be switched with 1 over a. And there's also the difference that u of negative n is active and equal to 0, whereas u of negative n minus 1 is not. So that's why I didn't get the same thing. I thought I would, but I overlooked those two differences. Okay. Convolution property is simple. What should it say? If I take the convolution of two signals, what should be the z transform? That should be like, at the end of this course, the only thing, if everything else is forgotten, this should not be. Most likely you'll not want to do any convolutions anymore, but at least you should remember this. This is the way out of convolution. How can you not remember? I mean, this is an easy way out, right? Just take the z transforms, multiply. All right, so we saw analogs of this in Fourier transforms, in Laplace transforms, continuous, discrete, everywhere. So that's one of the key features of the key purposes for transforms in the first place. So differentiation of the z transform we discussed, that amounts to multiplication of the time signal with n. So one final property is the initial value theorem. So if I give you x of z, without actually doing an inverse z transform, you can tell me x of 0. Oh, I need to give you one more property. I gave you x of z, and I tell you that this signal, x of n, is 0 for n smaller than 0. Okay? So how would I get x0 from x of z? Okay, so it turns out, you can do it the tedious way, do the inverse Laplace z transform, find x of n, and substitute n equal to 0, get the answer. But that's an unnecessarily lengthy way of doing that if all I care about is x of 0, right? So alternatively, I can remember the definition of x of z and keep in mind that this is the case. So that the summation that gave rise to x of z started actually at n equal to 0 because the signal is 0 before that. Okay? So x of n, z to the negative n, right? If I expand this, it basically says x0 plus x1z inverse, 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the negative n, right? 1 over 2 times z to the nega plus x2, z to the negative 2, etc. The term that I'm interested in is this. How do I get rid of the remaining terms and extract x of 0 out of x of z? How do you eliminate those terms? Is there a particular value of z that would make those terms go away? If you take z to infinity, all of these will go to 0. So limit z going to infinity as x of z, and all of these guys converge to 0. So what remains is x0. So that's the answer. x0 is the limit as z goes to infinity of x of z. So you can look at all the examples we discussed, take z to infinity, and you'll see that you will recover x of 0. All right, interestingly, that's the end of today's notes. We have about 10 minutes, so I will stay here for questions. If you have exam-related questions, I'm happy to answer them. If you have even longer questions, I actually have office hours starting at 2, so that will blend into the office hour. All right? Oh, yes, general question. Okay, yes. This one? Wait, silent. Say it again. Oh, yeah. You're right, absolutely. Thank you. Okay. Any other corrections? All right, for questions, see me here.